Good day, everyone. My name is Saimab Akhtar, and today we will be exploring the mathematical equations of spatial temporal Kriging. Now, you might be wondering, what exactly is spatial temporal Kriging? In the simplest terms, it is a statistical method used to predict values of a variable across space and time. It's like creating a treasure map for data, enabling us to predict where and when specific values will occur. This is an integral part of geostatistics, the branch of statistics focused on Earth-related phenomena. Knowing the ins and outs of spatial temporal Kriging is crucial for anyone looking to make their mark in this field, as it forms the backbone of many geostatistical models and analyses. So, whether you're a budding geostatistician or a seasoned professional looking to brush up on your knowledge, this exploration into the mathematical equations of spatial temporal Kriging is for you. Now, are you ready to dive deeper into the mathematical world of spatial temporal Kriging? Let's proceed. Before we delve into the equations, it's important to understand the basic concept of Kriging. In essence, Kriging is a statistical method that allows us to predict unknown values at certain locations, based on the known values at other locations. Now, this might sound a bit like fortune-telling, but it's far from it. It's all about leveraging the power of data and mathematics, and it's widely used in fields like geostatistics, meteorology, and environmental science. The beauty of Kriging is in its ability to take into account the spatial correlation between data points. Unlike other interpolation methods that simply average the nearest data points, Kriging considers not just the distance between observations, but also their overall spatial arrangement. This means that it gives more weight to data points that are closer together and less weight to those farther apart, leading to more accurate predictions. Now, imagine you're looking at a map and you have data points at various locations. Each point represents a known value, say the concentration of a certain pollutant in the air. But what about the areas between these points where no data was collected? That's where Kriging comes in. Using the spatial correlation between the known data points, Kriging can estimate the pollutant concentration at these unmeasured locations. But here's the thing. Kriging doesn't just give you a single prediction. It also provides an estimate of the prediction error, which tells you how reliable the prediction is. This is what sets Kriging apart from other interpolation methods and why it's such a powerful tool for understanding complex spatial patterns. So, to sum up, Kriging is all about making educated guesses about the unknown based on what we already know, and it does so by considering the spatial relationships between data points. It's not just about filling in the gaps, but about painting a more complete and accurate picture of the data landscape. With this understanding, we can now proceed to unpack the mathematical equations involved in spatial temporal Kriging. In spatial temporal Kriging, there are several mathematical equations that we need to understand. So let's start with the first equation. This equation is the heart of spatial temporal Kriging, the semivariogram. The semivariogram is a function describing the degree of spatial dependence of a spatial random field or stochastic process. It's represented as JH, where H stands for the lag distance between 2 points in space. Now, let's break it down. The semivariogram is defined as half the expected square differences between values at two locations. In simple terms, it quantifies the dissimilarity between data points as a function of the distance separating them. The semivariogram equation is represented as GH equals sign 0.5 asterisk E circumflex 2. Here, E stands for expectation, Z represents the random field, and X is a location in space. ZX plus H and ZX are the values at the locations X plus H and X respectively. The left side of the equation, GH, is what we're trying to find, the semivariogram value for a particular lag distance, H. The right side of the equation gives us a method to calculate it. We start by finding the difference between the values at two locations separated by the lag ch. That is, we square this difference, giving us circumflex 2. This value is then multiplied by 0.5, which completes the calculation of the semivariogram for the lag H. The semivariogram forms the basis for Kriging predictions and is critical to understanding how values are related across space. It's like a mathematical lens that allows us to see the spatial structure hidden in our data. Remember, the semivariogram is just the start. It's the first step in understanding the intricate web of mathematical equations that make up spatial temporal Kriging. That concludes our first equation. Let's move on to the next one. Now let's look at the second equation in spatial temporal Kriging. In the realm of spatial temporal Kriging, the second equation is known as the semi-variogram model. This equation is a key component because it quantifies the spatial correlation among measurements. It's like a mathematical microscope helping us scrutinize the spatial temporal pattern in the data. So let's start with a simple version of the semi-variogram model. It's usually written as gamma of h, where h is the spatial lag or the distance between two locations. This gamma function measures the average dissimilarity between data points separated by the distance h. The semi-variogram model is generally parameterized with three elements: the nugget, the sill, and the range. The nugget is the value of the semi-variogram at zero distance. It represents measurement error or spatial variability at distances smaller than the sampling interval. The sill is the value at which the semi-variogram levels off. When points are so far apart, they are no longer correlated. The range is the distance at which the semi-variogram reaches the sill. Now let's add some complexity. We can also have anisotropic semi-variograms, where the spatial correlation depends not just on the distance between locations, but also on the direction. This is often the case in geographical data, where patterns might differ in the north-south and east-west directions. The semi-variogram model can be fitted to our data using various methods, such as least squares or maximum likelihood estimation. Once we have our model, we can use it to predict values at unobserved locations, which is the ultimate goal of Kriging. Remember, all these symbols and variables are just tools. They help us translate spatial patterns into the language of mathematics, so we can harness the power of statistical analysis to understand our world better. That's our second equation. We're making progress. Now on to the last one. Finally, we arrive at the third equation in spatial temporal Kriging. Now, let's dive into the third equation. As always, we'll break down each symbol and variable, simplifying the complex calculations into digestible chunks. First, let's look at the symbol sigma. This represents the standard deviation, a measure of the amount of variations or dispersion in a set of values. In spatial temporal Kriging, it's vital to understand the variability of the data to make accurate predictions. Next, we have mu, the symbol for the mean, another fundamental concept in statistics. It is the average value of the data set and helps to determine the central tendency of the data. This is a critical component in Kriging as it provides the expected value at an unobserved location. The symbol AE is used to denote the random variable. This is the variable whose possible values are numerical outcomes of a random phenomenon. In the context of spatial temporal Kriging, it represents the unknown value at a location that we aim to predict. Let's now consider sigma e, the sum notation. This is used to denote the sum of all the values in a set or series, which is a crucial part of the equation as it helps to aggregate the impact of all the observations. Finally, we have lambda, the Lagrange multiplier. This is a scalar value that helps in solving optimization problems where we have certain constraints. In Kriging, it assists in ensuring that the weights assigned to the observation sum up to 1. In essence, this third equation is a blend of statistical principles and mathematical optimization. It's where the magic of spatial temporal Kriging happens, allowing us to make predictions about unknown locations based on observed data. And that wraps up our exploration of the mathematical equations in spatial temporal Kriging. But before we end, let's summarize what we've learned. We've covered a lot today, so let's take a moment to summarize. We started with a broad view of spatial temporal Kriging, diving deep into its core concept. This set the stage for our exploration into the mathematical equations that underpin this statistical method. We dissected these equations into 3 parts, each one integral to the whole. Part 1 gave us the basic mathematical structure, the foundation upon which spatial temporal Kriging is built. In Part 2, we delved into the complexities of the equations, uncovering their intricacies and subtleties. Finally, in Part 3, we saw how all the elements come together, creating a comprehensive, cohesive picture of spatial temporal Kriging. The understanding of these mathematical equations is pivotal, not just for Kriging, but for a broader comprehension of geostatistics. Remember, Understanding spatial temporal Kriging and its mathematical equations can open doors to a deeper understanding of geostatistics. Thank you for joining me today. This is Simab Akhtar, signing off.